Hello everyone, welcome back to our channel. In today's tutorial, we are going to build something that is both very practical and powerful. We are going to discuss in detail about building an agentic RAG framework for assisting us to understand research papers. This RAG tool that we are building can read through complex research papers on physics-informed neural networks. So for time being, we are using research papers on physics-informed neural networks in this tutorial, but the concepts that we present in this tutorial are applicable for any kind of research papers actually. There are no restrictions. This tool can extract key technical insights and convert them into human readable notes like this, pull out the governing equations that were specified in the research papers, and even generate some runnable Python code, all with proper citations as we shown here actually. These citations refers to the document from which this particular reference has been extracted, or this particular code has been extracted like that. The main important aspect of this tutorial is that we are not going to use any heavy RAG libraries like LangChain or LangGraph, etc. Instead, we will be doing everything from scratch using plain Python and a few essential Python libraries. This gives us full control over the workflow, and you will understand exactly what's happening in every step. It is a multi-agent system that plans, retrieves, analyzes, and generates responses in a structured flow. So we are going to build this entire project in two phases. This is phase one, and this is phase two. In phase 1, we create the basic knowledge base by extracting, chunking, and embedding the research papers. And in phase 2, we develop a team of specialized agents on top of the knowledge base to answer questions like a domain expert actually. So let's get started with phase 1. So in phase 1, our goal is simple. Take a collection of research papers. As I said, we are taking research papers on physics informed neural networks in PDF format. In our case, we have taken some research papers. They are residing in this data directory. If you open this data directory, you have this raw PDFs directory. So here are our research papers actually. 1, 2, 3, 4, 5, 6. So total 6 research papers we have taken. So if you open all of these in our Edge, it looks like this. So these are our research papers. These are the kind of topics that we have taken in our work actually. So we will be using these papers in building our RAG tool. So I have written these notebooks with clear documentation. So this helps you understand every detail about this RAG tool actually without any problem. So as we said, our first step is to set up our toolbox. So in this tutorial, we are going to use PyMU PDF library. So within that, we have this FAISS module. So this library is for PDF parsing. And next one we are going to use here is sentence transformers. So this sentence transformers we are using for creating embeddings. And next is our FAISS library. So this is a fast vector similarity search library, and a couple of helpers like pickle here we will be using, and some libraries like pathlib, etc. to show. These are used mainly for saving the data, and here we are using this one special library called tqdm. So using this tqdm we get this kind of progress bars, etc. One key design decision that we have taken here is we use these lightweight libraries and a small embedding model called all mini lm l6v2. So these can run comfortably on any cpu or a simple gpu. This means the pipeline works for both quick prototypes, and if you want, you can scale up this to larger scale simulations. So as we said, the first step is to extract the text from the PDFs. So that's what we are doing here actually. This function here opens the PDF and loops over every page in the document and appends the text to a single string. So that's what this basically does is, so here we are giving the directories. So after we extract the text, here I am doing some quick test to see what it has been extracted. So this is the information that was extracted from this particular PDF. So there are much other things, but we are printing a little text here actually. And if you look at here, this is what is at the top of the page, right? And likewise, there are many extractions, and it extracted all the text without any problem. And then here in the next phase, after we extracting, our objective is to chunk this information into minute bytes that an LLM can easily understand and process. We split this entire text into 300 words with 50 words overlap. The overlap is very important for preserving a context. Research papers often have equations and explanations split across sentences. Without overlap, you risk chopping of key information and some intermediate thoughts actually. We also skip ultra short chunks, for example, few keywords that are available at the end of your document, since they rarely add value and just add noise to the retrieval. So with this information, we are doing the chunking here actually. So this is our chunk function. It takes the text and it splits the text into several chunks. And overall, from all the PDFs, we have got around 227 chunks. Okay, and after we generate chunks, our objective is to build a FAISS vector search index from these chunks. So this is where we are building. So as I said, we are using this all mini LM L6v2 from this sentence transformers. So this embedding model will encode all the chunks that we have generated, all these 227 chunks, into some dense mathematical vectors. So that's what we are doing here actually. We are just calling the embedding model from this sentence transformer function, and then we are encoding that into this embeddings variable using this encode function. And after that, we are performing some cosine similarity checks, etc. And then we are normalizing here the embeddings that we have processed earlier, and then here we are generating the index. This is searchable. So in total we have a total of 227 vectors actually. So we have a vector for each chunk. So after we build this index, so here I am running a small test whether we can able to access these relevant chunks or not. So here we are defining one small retrieve function. What retrieve function is? This takes a query and returns top k relevant chunks. Okay, and we are using the same embedding model, that one all mini LM L6v2 model, for encoding this query as well, and it is very important. You have to use the same embedding model that was used in generating the index. You have to use the same thing for embedding this query as well. This test is not just about seeing results, it's about spotting problems early actually. If you see or search for queries like a Burger's equation and get matches about wave equation or Fourier transforms with very low similarity, it's a sign that your embedding model or this pre-processing that we did before needs some adjustment actually. So that's what we are doing here actually. So we are giving a small query like how do pins solve differential equations. So our objective is to get some relevant chunks for this query. Okay, so it retrieved all the top chunks, and here we are printing all the top chunks. So these are the top how many chunks we have given. So we didn't specify any chunk number, meaning it defaultly takes this 5 chunks. Okay, so 1, 2, 3, 4, 5. So total it returned overall 5 chunks. So if you look at here, the score that we have got is this one, and along with that we have printed one confidence, and this confidence is evaluated like this actually using the score. So overall we have got around above 70% or near to 75% confidence. So this is not a great confidence score, but it's sufficient for our tutorial actually. So in order to get some higher confidence, you have to change the model from small to, you have to use some bigger model to generate this one actually. This is a very small model, lightweight and fast enough. So that's why I used in this tutorial. If you want more accuracy like 95% or 98% score or confidence, so you have to use some bigger models than this. So these are all the texts extracted that we have got. So for our query, how do pins solve differential equations? So it got some information about different techniques that were presented in the research papers to solve differential equations actually. So overall, the match is decent. So I don't see any ambiguity in this chunks that were retrieved. Okay, and after we complete this testing, next we are saving some data like the FAISS index that we just built, and along with that some metadata. This metadata, currently we don't have much information in this metadata, so we will be just having some information about the PDF, the title mainly actually. So this is our metadata. Okay, like that. So we get two files, namely .pkl and .phis in this vector store directory actually. So that I have created here. So after we save these two files, so here I am performing a small testing. So it's a reload operation. So whatever the files that we saved here, we are just reloading them and checking whether we have got all the 227 vectors or not. So it is saying like restored index with 227 vectors. So we got the information back actually, and this information we will be using in our phase 2. So think of this entire phase 1 as building up a real library actually. While you are setting up some library, what we do, we just gather the books and we label all the book racks into proper sections, and we index all books and keep all ready for performing the book search. So in phase 2, it can be thought of analogically as here we are hiring some librarians. So a set of intelligent agents who not only find the right book but also summarize it, extract and solve the math, and sometimes they even write code based on the information that was presented in the math. That's it actually. So let's start with phase 2. In phase 2, the first step is about loading the phase 1 outputs that we are doing here. So we are loading both the pickle metadata files and files index from the disk. So immediately we verify counts. The number of chunk texts must match the files vector count. If not, that's a sign of mismatch or partial saves actually. So we log any discrepancy so it can be fixed before running our real queries. This upfront validation means we do not waste LLM calls on broken retrievals. So at the end of the day, LLM cost money, right? So we should not spend money on unnecessary things. So here we have got 227 chunks and metadata also 227 entries, and the FAISS in total also 227 entries in this index. So we have got all the elements that we have saved in our phase 1 actually. So there's no problem. So next is our embedding model and retrieval function. So we are going to use the same model, all mini LML6 V2 model, to retrieve the relevant chunks. So here I am giving the default of 6 chunks, and then we are going to extract some information from the loaded files like text and the source. This comes from metadata and this comes from the chunk, and these two we evaluate here actually. As I said, score as higher it is the better. And the next is index position in the chunk list. IDX. So for example, it loads 6 files, right? For example, so we will give a number 1, 2, 3, 4, 5, 6 after sorting, so that it will be easy for doing the reference. So here we are building this embedding model and retrieval function actually. So here we are using the same 10 sentence transformer and generating this embed model. Here we define this retrieve function. This retrieve function also uses this cosine similarity, and it returns some text, source, score, IDX variables. Okay, and this is how we define. We just embed the query using this encode function, and then we perform the search and we retrieve some relevant numbers from this search operation. And after we get that, we extract the chunks and then we store this source information into the source and then score IDX etc. Actually after that, just for sanity check, we are printing some information here actually from each retrieved chunks. So what we are doing here is we are just printing out for just 3 chunks. So since we are retrieving only for 3 here in this smoke test, so here we got a score of 0.627, 0.571, 0.535, and this is the information text that we have got actually. After we build this retrieval function, so next we will go into this citations. So just to make a point, this D and I has everything we need actually. So D has here we extract the score from this D, and I has the indices that were extracted. So you can use these indices and retrieve the information from these chunks using the index. So it has 220, it has 227 entries, right? So using this indices, you can just extract the informations that we need actually. After we build our retrieve function and embedding model, so next is that we are creating some helper functions. So this one is generate citations from the retrieved chunks. It's a helper function. So here what we are doing is for every retrieved chunk, we package the details like source file, similarity score, index number, and a trimmed snippet into neat citation format. This snippet is short enough to read at a glance but still shows the context so the viewer knows from where the answer is coming from. So here hits represents the list of dictionaries returned by the retrieve function, and cites, this one represents a list to store the formatted citation entries. So after we build this helper function, so this is just for our convenience, we are writing this call LLM and open router API. Okay, this is a very important. So this is our main LLM gateway. So in our this tutorial, we are using this open router model actually. So open router is a kind of supermarket for all LLMs. So here you have many LLMs like ChatGPT 5 or OpenAI APIs or any Claude, DeepSeek or many LLM APIs are available. So you can access any of them, and the cost is based on the kind of LLM that we are using. So it is charged based on the input and output tokens. Okay, so here we are using this LLM model from DeepSeek chart model v31. Okay, and I have specified my open router API key in my environmental variables in bash rc. So the advantage of using this open router is you can use all the LLM APIs through one API key from this open router. You don't need to specify a separate API keys for each model, like if you are using Claude, OpenAI or other DeepSeek models or any other. So all you can access through this one unified API key. And here I am setting this LLM mode as open router. If you do not specify this open router, it uses this stub output. So stub output is some just generated garbage output. So mainly when you are developing something, right, you no need this open router while you are doing the code. So only when your complete code is completed, then you can use this open router, because whenever you use open router, it charges you some money actually. So that's why I'm specifying this stub. If you do not specify this, it generates some garbage output. Okay, the garbage output means it is not really a garbage. It is made of these two things actually. Stub output plus the prompt 300 characters. So why it is written like this is because to verify if your code is doing correct or not. So if your code is correct, then it just prints this. If your code is wrong, then there must be some mistake, but that mistake is not related to LLM. Okay, once your code is ready, then we will inject the open router keyword here actually. When we inject the open router keyword, then the response that you got is from the LLM, not this garbage output. Keep that in mind. And here we are defining the URL. So this is the main target URL, and here you have to define this open router API key. So basically these are the two things that we need actually, and we don't need these remaining things, but these are essential when something goes wrong. So when something goes wrong, you have to try to understand how many tokens it consumed, how much money it got consumed, etc. actually. So this is very essential in gathering such information. And here we are defining our main payload. So what we are defining here is, so this is our open router model that we are specifying. So as I said, we are using this DeepSeek chart model, and here we are setting up the system message. System message, we are setting it as your precise grounded scientific assistant for pins. So I have defined it as a very small, but if you want, you can write a very big system messages comprising the entire personality of how this grounded scientific assistant looks like. So you can define all those things in the system format, no problem. And here you are writing this user prompt. This prompt we are sending to this LLM actually. This comes from the agents, and then the max tokens that we are specifying here, and then the temperature. As you know, this temperature is the creativity factor. So if it is 0, no creativity, and if it is anything greater than some 0, you can expect some level of creativity. If it is 1, you can expect a great deal of hallucinations as well. Here the default maximum tokens are 900. So here I have to mention about one thing actually. In LLMs, any LLMs, you have two categories of LLMs actually. One is the chart model and the other one is the reasoning model. So chart models are a kind of things like they take some input and generate some output in one go. But reasoning models are different actually. They are based on some chain of thought process. So internally, before generating our final response, it generates some intermediate responses, and the tokens for those intermediate responses are also charged for us actually. So keep that in mind. So that's why I'm specifying this max tokens. So if the total consumed tokens exceeds this particular limit, so you won't get any output. Okay, keep that in mind. So that's why you have to always use chat model. But if you want to use reasoning model, you can definitely use it, but you have to specify a very great number of max tokens. Keep that in mind. And then here for sanity check, I am printing this information like what is the kind of open router model and max tokens and temperature. And then here we are setting up some information. So I'm doing 2 attempts. So here this request is our main thing that we communicate to the open router. Request dot post with the URL and the headers and the JSON payload that we are sending actually. This is the main thing, and R is your response. Here I am printing some information from the R. Okay, so here we extract some information from the data, this one. So this data is retrieved from this R. So R is a response that has many things actually. So we don't need all of those things in our work. We generally need the main text that we are interested in. So that's all. So that was stored in this content, and we will return this content from this for loop actually. So we are running this retrieval process 2 times actually. So if the first attempt fails, so then you will get the response in the second attempt. When the second attempt also fails, you will receive an LLM error. So, okay. So after we build our main call LLM function, here we are printing some information like LLM mode, model, and key set, whether the open router API key is set or not. This is just for a sanity check. And here onwards our agent work starts actually. So first we need to define agent state and logging utility. So one of the key things is when we are having many agents, so each agent does some work. So here agent state is a kind of centralized space where all information that was retrieved from each agent will be put, and any agent can access that information actually. It is that kind of centralized space. So here in this agent state class, we are specifying the query, the plan, and the notes text, math text, code text, eval text, citations, and log. So this each one is generated by each agent actually, and query is the one that we put. Okay, and we are defining one add log function. So add log function, this puts the information in these variables actually. Okay, so this is a think of it like a centralized space. So this is very helpful because if you want to use the output generated by one agent, for example, this paper analyzer agent in another agent like evaluation agent, so this centralized space helps there. So after we build this agent space, next step is a helper function. So this takes the number of hits, so the kind of chunks that we have retrieved, and put them in a format actually in a stack. It is just a cosmetic purpose, just for sending it to the prompt. So we use this evidence, we directly send this evidence to the prompt. So if you look at here, for example, a information that we are sending to the prompt, so this is our evidence actually. This information is formatted in that build evidence function. Okay, this evidence formats in ways actually. First one is a number and a source and the text. So if you look at here, anything, it has two things, right? First is the number and the second is the PDF name, followed by the text. It has much text, but I'm just printing a part of it. Okay, this is what this build evidence function does actually. Once we complete this build evidence function, next our main agent definition starts actually. The first agent is the query planner agent. This query planner agent decides which agents to run based on the query. This is very important. For example, here this paper analyzer agent is the first one and always runs first. And the citation agent here is the last agent. And optional agents in between like math, code generator are triggered if the query hints at them. For example, keywords like derive, equation, and like boundary, these are some keywords that we are using to trigger this math agent, and some keywords like code, implement, template. So these are the some kind of keywords that we are using to trigger this code agent. Okay, if these keywords are not there, then these two agents will not be triggered. Okay, and in the end we have this metric agent, we have this evaluation agent, so it is triggered based on these keywords actually. So here we are organizing this agent calls in a specific keywords based, but in our upcoming tutorials we will introduce another agent so that is more intelligent enough and picks agents like math agent and code generator agents in more adaptive way. For example, these are not just the ultimate keywords, right? So there may be many other keywords in which math agent is essential, but we are not we are not triggering the math agent if that keyword is not available in this list. So in such case, so we need another higher level agent so that decides which agents to go. That will be a sub agent in this query planner agent. Okay, so for now in this tutorial we will use these keywords to decide which agents to call, and this query planner agent decides that actually. So it sets what agents to call, and whenever it decides upon some agent sequence, so it stores that agent sequence in this agent state that we have created. So using this add log function, you can access that actually. And the next is our paper analyzer agent, which is our very first agent. This paper analyzer agent retrieves the top relevant chunks and produces a structured technical summary like the key claims, setups, losses, training tricks, etc. Actually, we are not giving any chance here. Actually, we are defining every guardrail and every information that we expect in the format that we want. We are mentioning every detail actually. So for example, if you look at here, we are defining this agent prompt like this. You must write a brief grounded markdown note. Use only the evidence. Okay, here we are giving some markdown and formatting instructions, and then here we are setting something like this actually, return exactly this structure, and here we are sending the evidence. Okay, and then we are doing some debugging sanity checks. So before calling this LLM, we are asking to print the prompt that we are sending and to print the response that we are getting. Okay, mainly the length of the response that we are printing here, and then we are just printing some warnings like if the response is empty, then we will just print like paper analyzer produced empty output. Okay, this is the kind that we are doing. Once we retrieve the text, we are sending the information to the agent state, that is the centralizer space, using this add log. And next here we are doing some connectivity test. So we are just testing out our LLM. So call LLM function, we are sending some prompt, return only the word OK, and we are giving some maximum tokens as 4 and temperature 00. So if the LLM triggers and returns OK, then this one will be done. It prints OK, else it will create an error. Okay, like that. And the next is the math agent definition actually. So what does this math agent does is, so it extracts the mathematical equations if there are any in the evidence. So your evidence looks like this, right? So your evidence looks like this. So if there are any mathematical equations here, so there are many mathematical equations here, right? So this math agent will extract the equations from this and put it proper order. Okay, it extract the information from all these evidences actually. That's what we are doing here. So here extract grounded math spec using only the evidence. If a part is not present, output unknown. We are giving very explicit output instructions actually, and here we are giving this instructions for the markdown, and here we are asking to print these equations in this format. If something is not available, it will print an unknown there. Okay, without hallucinations, etc. Here we are sending the evidence, and as I said, here we are extracting the text and then we are sending the text to our agent space. So this agent space is very important. It is a centralized space where every agent puts and takes some information. And the next is the code generated agent. This code generator agent works on top of this math agent actually. So this code generator agent tries to develop code based on the equations that we retrieved using the math agent. So that's what we are doing here actually. We are giving a prompt, generate a compact prompt using PyTorch pin skeleton as a single fenced code block, and we are giving some instructions, and we are sending the math text that we have from math agent actually. You see here we are sending this math text as state.agent. State is a centralized space. Okay, keep that in mind. So it generates some sort of code. Sometimes it works and sometimes it won't work, but the main idea is to give you an idea about how to code this. It will definitely give you all the details that are necessary in the code. Okay, And then we are sending this code text also to this agent space, and then we are generating our next agent, that is evaluation agent. This evaluation agent searches the papers for experimental setups, metrics, and results like RMSE, relative errors, optimizer comparisons, etc. It summarizes patterns, example how switching from Adam to LBFGS improved accuracy, or how increasing collocation points changed convergence. So it extracts this kind of information actually. So we are just using this note text within the prompt, and this context, and this context is retrieved here actually. It is based on this source and text. So that's it. After we build our evaluation agent, next is our last agent. This is our citation agent. This citation agent pulls every citation from the previous agents and then deletes any duplicates, and then produces a clean and unique list. This ensures the final output cites each source only once, even if multiple agents reference the same chunks. Next, after we build our citation agent, so next objective is to build this rendering and agent pipeline actually that we are doing here. Okay, so before that we will do a small sanity check of on these agents actually. So here we are calling an agent state. So agent state, we are setting a query like summarize governing equations and BCs for Burger equation and give a PyTorch template. This is the query that we are giving, and we are sending that query to the agent state query, and we are extracting that yes, and we are sending that yes to this query planner agent. So from the query planner agent, we expect to see the plan and then the retrieved text. Okay, so here if you look at here, this is the query that we are sending to the query planner agent, and this query planner agent decides based on this query, it decides this agent plan. Okay, paper analyzer agent, math agent, code generator agent, and citation agent. These four agents it set up. So if you look at here in our query, there are no terms like metric or error, RMSE, MEA, etc. This kind of information is not available in our query planner agent. Hence, it skipped that evaluation agent. So it only consider only these four agents: paper analyzer agent, and we have some terms related to equations. Hence, it called math agent, and we have this template and PyTorch. So that's why it called the code generator agent. And definitely site agent and paper analyzer agent, the first and the last will definitely be there. And the next, it hits 6 research papers, and it total overall we have got 10,519 characters in the evidence. So overall the 6 evidences consist of these many characters, and when we send that to LLM using this prompt. So this is our prompt actually. This is the prompt that we are sending in the paper analyzer agent. So these are the complete evidences that we are sending. So overall we are sending out this much characters in just the evidence actually here. From here to here we are just sending some 10,000 characters. Apart from that we have some more text, this one. So this entire prompt further use it to calculate the total number of tokens, and your cost will be evaluated based on that. So from this prompt it generated some response, and here is our response. So I have not printed the full response here, but it generated a response of 2420 characters actually. Okay, one key thing to understand here is if you look at this response within the claims, physics based neural networks, here is like this, and within the setups we have got some text like this actually. It is good, but it's not readable. We cannot understand anything. It is all like a code actually. The response is also in the form of a code. So here we need to render this into proper human readable form. Okay, that's what we are doing here actually, rendering and running the full agent pipeline. So here we are creating a small markdown generation function. So using this function markdown on display, it takes the text from the markdown code and it generates a markdown response based on that. Okay, so here we are rendering it actually notes text, we are sending it to this, and this here we are generating the markdown display for this one. So likewise for each math text and evaluation text and all other citations. So we are generating this markdown display for this note text here, math text here, and code text here, evaluation text here. And then for citations, we are just printing it normally. It is a normal text, right? So there's no confusion there. Generally citations looks confusing and we will take that as it is. So we are not using any markdown special display for that. And then here we are running the pipeline. So this running the pipeline is same as that we did earlier, just the kind of things that we did here. We are going to do the same things in this query pipeline as well. So we are sending a query to this run pipeline, and we are sending that query to the agent state, and we are retrieving that here in the state. So first we are setting and retrieving. Two things are happening here actually. And then we are sending that state to this agent planner query. And then this query planner agent plans and executes the things that we need. And this returns some responses automatically, and all the responses will be put in the agent space. Okay. And here in this render output, we are taking that entire agent state and extract the information that we need. The information that each agent generated is already available in our agent space, right? The centralized agent space that we have created, and we are just extracting that here actually. And the final, it returns the state. And the state, no need to use it, but this gives us some information, and we are not using that information in this tutorial. We are just interested in the final output that we got from the LLM. So that's what we are doing here actually. So let's run it. These are all some of the sample queries that we are running. As I said, we are interested only in the output generated by the run pipeline function, but we are not interested in what this function returns actually, the final variables that is returning. So that's why I'm taking it in an empty variable. Okay, here, but it has some good debug information actually. Whenever some things go wrong, then you must be look at this particular thing actually. You have to save this to a variable, and you have to look at what is available and what are the values that it got actually. So since our information is good, so I'm not going in detail there. So here, when we call this run pipeline function with this summarize governing equations and basis for burger pins and give a PyTorch template, so the same one that I gave earlier. So we are sending out this much prompt, and then the answer that you got is printed like this in a markdown and human readable way. These are the equations that it is extracted, and these are the losses. These are the training tricks that are available in the extracted chunks. Okay, and then this is our simple PyTorch template, and this template is also extracted from the code. For example, here this code is adapted from TensorFlow code in 4. So what is this 4? This 4 is referenced here. This is RISE 2019 paper, and that is this is our RISE 2019 paper. So if you look at here and goes to the end, this is not our Burgers equation, and yes, this is our Burgers equation. So you have this equation here, and this is a small code snippet also here. So in your response, you have got the code snippet only, but in a different, we restricted to use PyTorch and generate the detailed code snippet, right? So it generated this, and this is the equation that you have just seen here. Also, it used its internal knowledge and generated this general form. Okay, likewise, this is some of the losses. So it's not like it generates only the thing that were available in the research papers. So it uses the information as a context. Sometimes it generates as it is. Also, sometimes it uses its own knowledge that this LLM has actually. So you will get this final response like this. And here, these are all the main equations that were available in that. And these equations you can code in this format. So this is the kind of information that you can get from this agentic RAG, which is very highly specialized and little costly, and it is more effective than the RAG, the vanilla RAG, the normal RAG that we have seen earlier in our other tutorial on Ask PDFs. And next, we will try this in another prompt. So summarize governing equation. It is also a same prompt actually. So what we did is we just used it whether we get the same response or not again. So again here also we got the same response but in a different format. Okay. but the response is same. So this is how actually, this is the point here to understand is whenever you run LLM, so you get different responses actually. Even if you use the consistent prompt, you get a different response. This is one key thing that you have to understand. And in the next, we used a different prompt, derive the residual loss for a wave equation pin and evaluate typical metrics used. So here this is the prompt and this is the evidences that we are sending inside the prompt. And here if you look at here the agents that we are using as paper analyzer agent, math agent, and here you see this evaluation agent. In our earlier response we don't have this evaluation agent, and now you see this evaluation agent because this evaluation agent appeared because you used this metrics keyword. Okay, and now the response is like this actually. This is your claims that you are making, this is the wave equation, and this is the loss function. These are the some training tricks that were available, and these are some evidences, and this is the main text, and there is no code agent, right? So you have not asked for a template, so it didn't give you the code. And in the next prompt, provide a pytorch script to train a pin for a Laplace equation. So if you look at here, it asked for a paper analyzer agent, math agent, code generator agent, and citation agent, and no evaluation agent here actually. So it generated this response on the basic equation, Laplace equation. So likewise, here is your final math specifications, and here you see the boundary conditions, the loss terms, and the final generated code. Sometimes this code may not execute, but the key things that you have to understand is the kind of logic it is generating actually. This definitely give you the skeleton, okay, that you need in your work. So you just have to work on each element of the skeleton to get the desired result. Okay, here it did not implement this things, right? It gave you some to-dos. You have to work on it. And if you want, we can create another agent to work on this to-dos as well. So that is the main thing here actually. And next here we are sending another agent, compare reported results and errors from heat equation from pins across papers. So here we are sending this chunks, and then we are getting these responses. Okay, so no code here, so it doesn't have any code generator agent in action, it seems. So yes, evaluation agent is here, but code generation agent is skipped actually. Yeah, that's it. This is our overall tutorial. So we build everything from scratch using some basic Python libraries. We included all steps in this tutorial to generate structured insights and runnable PyTorch code from the research papers. This design is modular, so change the embedding backend or run a local LLM you want in a different way actually. You can change the LLM to a higher LLM, or you can use that embedding model into something more advanced actually. That's up to you. I used a free embedding model, but the LLM that I used, this DeepSeek one, it is chargeable. Okay, so Open Router charges you some money for that. You can use some free models in the Open Router LLM actually, but free models are not really free. You have some call limitations. You cannot call unlimited number of calls in a given time span actually. There are some limitations. I guess there are some, you can only make 10 calls in 1 minute. So that kind of limitations are there. In agent space, right now in one single run, we call how many times LLM. So if you look at here, we have 4 agents here, paper analyzer agent, math agent, evaluation agent, citation agent. So in one single run, we call this 4 agents, and each agent calls the LLM separately. Okay, so 4 agents. So in this one agentic run, you call LLM 4 times. Keep that in mind. So agentic RAG is a little costly, and you have to be very careful about how many times the LLM is called and the cost structure, which we will discuss in later actually in our later tutorials, how this cost is evaluated and how can we optimize the cost. Okay, which we will discuss in our later tutorials. So if you found this tutorial useful, please like, subscribe, and comment your suggestions or have any questions. Okay, thanks for watching. Happy learning.